works in robotics and haptics and manipulation and adjusting. She studied in Berkeley, and then she did her PhD at Cornell, and she's now professor at UCLA. And I have to say, she is one of the 25 most notable women in robotics. So it's my pleasure to give her the stage. And thanks again for coming.
Oh, I'm so sorry that I have to present this remotely. I was looking forward to hanging out with everyone and really presenting this in person, but the universe said no. But at least I get the chance to take today to share some of the perspectives that our lab has about the role of touch in robotics. Okay, hopefully you see some little movies of artificial hands doing interesting looking things. And the reason I wanted to start with this is to point out that modern artificial hands are now capable of mimicking many complex movements of the human hand. But what we really like to think about is what is movement without touch? And so I thought I would start this talk with a nice segment from Miles O'Brien's visit to Dustin Tyler's lab in 2014 to give you a flavor of the way that we think about touch.
Science correspondent Miles O'Brien had much of his left arm amputated last year after an accident while on a reporting trip for the NewsHour. He has since been exploring leaps forward for modern prosthetics.
And feel free to adjust it as needed, okay?
A hand without a sense of touch isn't really a hand at all. It's more like a pair of pliers. Watch blindfolded hand amputee Igor Spetic try to pick up some blocks using a prosthetic without a sense of touch. It's not very productive.
That was no sensation.
No sensation.
And so you were just
going blind.
Just
literally going blind.
Yeah.
Now watch what happens when the sensory perception is turned on. It's like night and day.
But then when I grab it, if I grab it just right, I feel all three fingers. If I grab it right, or two fingers, then I know I have it, and then I'll move over and drop it.
Is it your phantom hand that you're feeling it in, or is?
Oh, it don't feel phantom to me when I grab a block. To me, it does not. It feels like my hand. It feels like something between my two fingers that's vibrating.
For Igor, who lost his hand in an industrial accident 4 years ago, something powered by a battery and made of plastic, metal, and silicon can become his hand.
So perhaps I'm preaching to the choir here, but we believe that touch is useful. Whether you're dealing with robots that are working within the human body, on the human body, in very close proximity to the human body as for assistive robotics or manufacturing, or in extreme environments, search and rescue, handling of dangerous materials such as nuclear decommissioning, underwater, or space. And vision is especially important for planning, but there are many times that vision is limited or entirely unavailable. So for example, putting on a bicycle helmet, you do not have a direct line of sight to the pieces of the helmet that you're trying to put together. Or maybe the hand or part of the object, the hand is occluding the object that you are manipulating. Maybe you're reaching around in the dark for that light switch behind obstacles or inside your pocket or your backpack. We can also talk about extreme environments such as in smoke or in turbid water where your vision is very occluded. You can also consider not only extreme environments, but extreme objects such as highly deformable objects like rope, thin sheets, or bulk deformable materials for which we don't have analytical models at the same time that we are manipulating these objects. And then you can imagine objects that are both deformable and maybe animate, and we don't know exactly what they're going to do next. And then I thought I'd round out this collage with one of the holy grails of dexterous manipulation, which is in-hand manipulation. So the next thing I want to talk about is touch being multifaceted. And I know that you're going to have a Professor Sliman Benzmaya speaking to you later during this workshop. So he'll tell you a lot more about the biological mechanotransducers, but just if you take the basic textbook approach to this, we have our superficial as well as our deep mechanoreceptors. We can also categorize them into our fast adapting and our slow adapting. And I would argue that most of the tactile sensors that we have now, or at least the ones that my lab has worked with, don't even come close to the beauty of the biological mechanoreceptor. A lot of them are very primitive, but we can still do useful things with them. And so I thought I'd show you the variety of tactile sensors that our lab works with. And we're agnostic in that sense. I don't believe personally that there's any one tactile sensor that will work for everything unless you're going to grow a new fingertip, for example, biological fingertip. But in the meantime, you need to take into account cost, application, robustness, the size of the system that you're adapting to, and so on. And so I'll start out with some of the low-cost DIY tactile sensors. These are using piezoresistive fabrics that respond to stretch and pressure. We've also embedded barometers, the same types of barometers in your cell phone. We've embedded them in elastomer, and you can use these as pressure sensors or force sensors. And this is work inspired by Rob Howe and Matej Chow-Carley. And Matej Chow-Carley's group actually took an array of these barometers, and if you tilt them at angles, then in theory, you can back out 3D forces. I also have a long-standing collaboration with Jonathan Posner at the University of Washington on microfluidic tactile sensor skins. And what we've done is taken liquid metal and used them as wire paths. And so on the left-hand side, you see our very first iteration where each of the taxels, or a tactile analog to a pixel, is existing wherever you see a vertical wire passing over, not intersecting with, but passing over a horizontal wire. And that creates a little capacitor that is then sensitive to normal force. More recently, we've gone to a resistive-based approach. So we can use the spirals shown in the lower right-hand corner. And that's for isometric normal force sensing. And we can also use pairs of these rectangular serpentine sensors on either side of the nail bed to extract shear force. And so with multiple pairs of shear force sensors, an array of normal force sensors, we now have 3D force. And it turns out by moving from a capacitive based approach to a resistive based approach, our bandwidth increased to about 800 hertz of vibration that we can sense. And one of the interesting things that we found, actually through work with a different sensor I'll show you later, is that it's really interesting to put tactile sensors on areas of the fingertip that do not make contact with the skin, which is with objects, which is kind of counterintuitive because you would think as you're designing a tactile sensor system, you would obviously want to put them where there's going to be contact and touch. But if you're trying to back out things like shear force, you can sense the stretch of the finger pad in other places. For example, near your own nail bed, as you put your finger down on a table and shift it left, right, leaving the rest of the finger pad where you are going to have direct contact available for the normal force taxels. We've also taken the multimodal, normal force, shear force, vibration sensor, and we've been working on marinizing it for use in the ocean at depth. The versions on the left-hand side, I just want to kind of show you the messy evolution of this skin as it started out as something flat that we wrapped around a 3D printed finger that now we have encapsulated in a larger finger cot or glove. That's not the latest version shown in white there, but these are the figures that I was allowed to show. We're working directly with RE2 Robotics, which was recently acquired by Sarcos Robotics, that produces robots for underwater infrastructure maintenance and explosive ordnance disposal. So we're excited to bring tactile sensing to underwater environments. We also have a collaboration with Ted Adelson, and so we have access to a few of their different gel site and gel site wedge sensors. If you're not familiar with the sensor, I think you're going to have Professor Yuan speaking to you later in this workshop as well, and she can tell you a lot more about how the gel site is constructed. But very briefly, it's a finger pad with an elastomeric finger pad. On the back side of it, you can put an array of markers that you want to track. And then the finger pad is illuminated internally with different color LEDs, and there's a camera in there that samples at 30 frames per second. And you can track the optical flow of the inside of the finger pad to infer how the finger pad is deforming. And they've written code to back out things like force and torque at the finger pad. We've also been working to recreate the open source meta digit. My lab, inspired by what Ted Adelson's group has done with the gel site, was we created a new procedure to add some custom internal finger pad markers so that we could also track that type of optical flow from the inside of the digit, and we've adapted them to multiple grippers in our lab. And finally, the tactile sensor you'll see most in this talk is the SynTouch Biotech, which I worked on when I was a postdoc with Jerry Loeb as part of the DARPA Revolutionizing Prosthetics program. The finger was designed for prosthetic hands and was designed in a bio-inspired way, where the core of the finger is like the bone of your finger. There's an elastomeric skin that's inflated away from the core by conductive fluid. The skin actually has a fingerprint on it to enhance vibrations when you're touching textured objects. And the skin is inflated away from the core by conductive fluid that we then tap into with a pressure sensor. So now I have a hydrophone. And we can sample that hydrophone at 100 hertz to get a crude measure of overall fingertip force, or up to 2200 hertz if we want to back out transient information and texture signatures. There's a thermistor in the fingertip that you can use to measure the rate of heat conduction away from the finger to infer material properties. But where my lab has found we've gotten the most bang for the buck is by looking at this array of impedance electrodes that sits on the core of the finger. And I'll show you images later of the core without the skin on, so you can see these electrodes. There's only about 19 of them. But by tracking the spatial temporal changes in impedance, we can back out changes in the bulk finger pad shape as we're touching different objects. So everything I showed you just now is about, the hardware to collect tactile sensor data, but I would argue that that's not yet touch. We still have to abstract these tactile sensor data. So touch is also abstraction. We need haptic perception, and that necessitates the abstraction of these raw sensor data values that are generated by known actions. And so taking inspiration from this classic Liederman and Klatsky paper, we perform exploratory procedures that have been identified with human psychophysics experiments. So I can't see you all right now, but if I asked you, how rough is the chair that you're sitting on? Think about how you would answer that for me. And I'm guessing some of you are maybe rubbing your fingers along the chairs that you're sitting on. And that's the point, which is that if there are certain material properties that you're trying to extract from an object through touch, there are very classical exploratory procedures, or EPs, that we have learned to do to extract that information. So moving your finger across surfaces to extract texture, pushing against objects to extract information about hardness, wrapping our hands around objects to learn about global shape, and so on. And so some of our early work was simply playing out exploratory procedures on our sensorized robot test beds, and you'll see this green biotech finger in a number of these videos. But we're basically, sliding, performing static contacts, doing wrist rolls. And back in the day, we were using support vector machines to classify edges, the orientation of an edge with respect to the body. For example, if you're reaching into your pocket and you're able to find the edge of your cell phone and trace that edge to the power button, these are basic capabilities that we would want a robot to be able to do as well, to orient their body towards salient local geometric features, also including bumps and pits of different sizes and shapes as shown on the right. More recently, we've done work to estimate or perceive tactile directionality. And so this is work done by Dr. Gutierrez. And the idea is that when you're holding an object and something perturbs that object, even with your eyes closed, you can tell the direction of that perturbation or force on the grasped object. And so we trained a convolutional neural network to back out that angle of tactile directionality. And to collect the training data, we flipped the situation. So instead of perturbing the object, we have the object sitting still, and then we move the fingertips relative to the object. And as you can see on the video on the right, you can see the finger pad physically deforming, and that will be reflected in the electrode spatiotemporal data that will then train our neural networks on. So in the upper left-hand corner, you can see the BioTac core without the skin. Those shiny circles are the individual electrodes, which are also shown as the blue dots in that plot just to the right. And on the z-axis is the change in electrode impedance. And whenever we see a positive change, we know that the skin is getting compressed toward the core. Whenever we see negative change, we know that the skin is bulging away from the core. And this is happening over a continuum. So even though we only have 19 electrodes, we interpolate, and then we turn those into grayscale pixels so that we can leverage, all the convolutional neural network algorithms that are already out there for images. And then we train them and can use these neural networks to basically recognize the patterns in how the finger pad changes based on the different directions. And we trained one neural network to give a point estimate of the angle, and then a second neural network to give an estimate of the variance or the uncertainty about that angle. And this is showing the real-time use of the trained algorithm. And in that short clip there, the robot was programmed to not let go of the object until the robot sensed a force toward the palm, or actually away from the palm, as if someone was trying to take the object away. Here's another example where we're setting down an object and the robot was trained to release the object as soon as it felt that upward force as the grasped glass interacted with a support surface and pushed upward on the fingertip. One of the more interesting things we've been doing recently is tactile perception within granular media. And this is fun for me because I think for years we've thought about touch in an open air type of environment where the no contact state is very easily discerned. But as soon as you plunge your hand into sand at the beach or whatever, now you're stimulating all sorts of mechanoreceptors all the time. And the tactile perception problem becomes one of distilling something of interest, like a buried object, from the tactile noise that's being generated just from moving your fingers through granular media. And so we took our same sensorized system and we raked it through a variety of different particulates, ranging from coarse sand to coarse gravel, or mimicking that particulate size. And we used a sparse fusion recurrent neural network to estimate whether you're contacting a buried object or simply running your fingers through, freely moving your fingers through granular media. And so what you'll see in this video, the main video is a side view of this finger that's going to be pulled across that buried cylinder. And then the lower left-hand corner, you'll see a belief map that gets updated with a probability of whether the fingertip is freely moving through granular media, shown in blue, or interacting with a buried object, shown in red. And this, of course, is just from a single exploratory procedure. And we have a second paper currently under review where we also propose additional exploratory procedures that are chosen specifically to reduce the uncertainty in the belief map over time. And one of the things that we discovered is that it has to do with granular media jamming. And I'm not sure how many of you are familiar with granular media jamming, so I'll just take a minute to describe it. As you're running your fingers through granular media or particulate, the granular media will act sometimes like a fluid, sometimes like a solid. If the particles can move out of the way, it acts like a fluid. But as the particles get jammed up and stuck against one another, as if you're trapping them against an object that you're approaching, what happens is the particles will form force chains. They'll start forming a chain that begins at the object that's buried, and it'll go all the way back to your finger. And in that sense, your finger will get tricked because you will feel an increase in force even though your finger is not directly contacting the buried object. And so for a while we thought, well, this is a liability because we're going to have to take into account granular media jamming properties to further reduce the uncertainty in our belief map of where something is buried, what its shape is, and all that, because the fact that we're feeling something that's not there yet is going to mess with the accuracy of our belief map. But turns out that if you think of it from a SLAM perspective, you know how mobile robots do SLAM with LiDAR and they're moving around simultaneously localizing themselves, but also mapping their environment. It turns out that you can use this granular media jamming property for proximity sensing. And so that's something that we're working on right now. We have this one paper in review, and then we also have another paper that we're working on granular media jamming properties. But the idea is that if you know where you are in this granular media jamming state, you can actually locate an object and learn more about, explore about its outline without coming into direct contact with it, which is desired, especially if you're looking for something that's dangerous, that's buried. So in this video, what I'm going to show you is the finger being raked through the sand. And we have highlighted for you the particles that are just shifting from frame to frame using white. And you'll see this field of white particles that moves ahead of the fingertip and will prematurely interact with that blue buried block before the fingertip does. And then you'll see that reflected force-wise in the upper right-hand corner plots there, where we have not only the torque measured by a load cell at the base of the finger, but also a force estimated by that biotac sensor. And where we think jamming occurs, you'll see a little red asterisk appear in this force plot. So right about here is where that front of failed soil ahead of the finger interacts with the block before the fingertip does. Okay, so the next point I want to make about touch is that it is expensive. And for those of you who have tried to simulate tactile sensors, you're probably familiar with how difficult that is and how the contact problem is a difficult problem to simulate. And so most of the time we're relegated to actually collecting data on hardware with tactile sensors. And that can be very time consuming for the student. It can induce a lot of wear on the robot. It just takes a lot of time, and there aren't millions of images that you can download if you're doing computer vision. We don't have an analog for that for touch. And so we have done a couple of experiments on how to use reinforcement learning to learn hard to code skills. The first one is closing a ziplock bag. So the system that we had on the left was a Barrett WAM arm with a Barrett hand. We put 2 biotacs on the fingertips. We set up a ziplock bag, and then we have a video camera there. And the video camera is not actually needed once the policy has been learned, but it helps to automate the learning process. On the right-hand side, I'm showing a video of just a naive pre-planned linear trajectory showing that without closing the loop using touch, we're not very effective at closing the Ziploc bag. Our fingers actually fell off of that blue zipper there. And so we believe that as you're manipulating this deformable object, if you want to think of the zipper as deformable linear object, it's moving as we are interacting with it, and it behooves us to close the loop using touch and to replan our next action based on our current state. And so in preparation for the reinforcement learning that we did, we first had to describe states, and we just said high, center, and low. We assigned rewards to them. So we tried to motivate the robot to keep its finger pad centered on the zipper. Otherwise, it would fall off and not be able to regrasp the zipper. And then based on a preliminary set of studies, we had only 5 actions that were biased in the way that's shown that the robot could do while keeping its fingers in the plane of the zipper. And then what we did was we allowed the robot to explore the state action space, trying different actions from different states and recording whether there was a reward given or not. And in this particular paper, we were comparing a resource-conscious reinforcement learning method called contextual multi-arm bandits against a benchmark of Q-learning. But the point is that, yes?
I have a question. Can you hear me?
Yes, I can hear you.
I'm just wondering, like, from naive perspective, I don't have experience in this, but just simply following the line, couldn't that be like achieved with some classic control algorithm? Why did you need reinforcement learning?
Oh, yes. Well,
seems pretty straightforward. I don't know.
Yes, I suppose we could just follow the line if we wanted to use vision. We were purposely doing this with our eyes closed, if you will, where we wanted to close that.
With tactile, with tactile sensor as well, you can see if you're drifting from the center with the tactile.
Oh, yes. Yes. Well, obviously.
Controller for that. Yes,
this was our approach to sensing whether the zipper was drifting, and that was using, because it's this biotech sensor and not something convenient like the gel site, we couldn't just look at pixels and know whether there was a line there and follow the line. Although what you're describing has been used in more recent work using the gel site for cable following. It's just that at the time we were doing this work, we did not have the gel site, so we had to have a secondary classifier to determine whether the zipper was, somewhere on the finger pad and where.
So in other words, what he's saying is you can't just obviously look at the electrode impedance and tell where the zipper is.
Correct.
Right. You could train a regression, a little MLP or something to do it, but you decided to do it with reinforcement learning instead.
Yes.
Okay. I mean, it can't be that hard to infer the position of the zipper, right? But this is reinforcement learning.
That's correct. And this was part of a new collaboration that we were working with someone who is, their bread and butter is contextual multi-arm bandits. So that's what we were focused on.
Okay, thank you.
So once the policy was learned, of course, you could turn off the video and just use exploit the policy that was learned through the exploration. And this is just showing that learned policy being tested on novel, more flexible Ziploc bags, now with loads and things like that. But it's, you can still see that it's fairly slow. The speed is not so much the inference as the motion planning. So I think if we could go back and do the motion planning a little faster, we wouldn't hit the speed of
Can I ask a question? No, can I? This is very interesting problem. It's a great problem to work on because everybody struggled with closing these stupid Ziploc bags.
Yeah.
Sometimes it's extremely hard to start, and you have to use your fingertips carefully to feel whether, do you actually use reinforcement learning to sense whether the zip has snapped together, or do you always get it started beforehand?
Yeah, so we did cheat by starting the zipper already aligned, but in the paper we show at the end, when there's that satisfying click at the end, we can feel that through the biotech. You'll see a little transient in the hydrophone data. So you can actually tell when you've succeeded.
Okay, but what you're doing is controlling the upward and downward motion of the arm to try to help it slide along the zipper? Is that, I didn't quite understand what you're controlling.
Yes, you're controlling those 5 different directions or actions in the plane of the bag.
Okay, thank you.
Yep. The second hard to code skill that I'll show you is part of a more recent publication, and that's flipping a notebook page. So we have, in this case, a Canova arm. We have 2 biotech sensors. So there's going to be a top finger and a bottom finger. We set up a binder, and my student wanted to test the policy on different contexts. So the contexts that we're going to be using are small binder pages or large binder pages. And the key to any reinforcement learning is to establish a reward function that not only leverages signatures and whatever data you're using to learn, but also is functionally meaningful. And so we included in our reward function the fluid pressure inside each of the biotachs, how the electrode impedance changes, as well as binder movement, which we wanted to minimize.
But why do you include the electrode impedance as part of the reward?
I'll show you in just a second. It has to do with the signatures associated with the electrode impedance.
Okay.
So it's a little bit artificial what we did here, but it's, we did it to demonstrate that you could learn dynamic motion primitives using tactile sensor data. And so what I mean by artificial is there are a lot of different ways that you could flip a notebook page or turn a page. And so we had to pick something that was ideal and then pick other behaviors that were less ideal and show that we could start from a less ideal trajectory, and that using touch only, that the robot can learn how to get back closer to something more ideal. And so the upper left-hand image is kind of a perfectly semicircular trajectory where you're turning the page, but you're not feeling these less desirable things, such as page warping, as shown in the middle. And I'll start the video in just a second after I orient you to this slide. But the page, if your semicircular trajectory has too small of a radius relative to the where the pages are bound, then you get all sorts of page warping, which you will feel at your fingertip. And that can also lead to snapping, which is a transient that we can also pick up through the biotach. Aggressive trajectories on the far right are when you often use too large of a radius, or you're pulling too much on the binder. And that's where the motion capture markers on the binder come in. On the bottom two plots, we have the two fingers. And so I just put them both here to show you that the top finger and the bottom finger experience different things, number one. And then if you look at the different electrodes in each of the fingers, each of the different parts of the fingers experiences something different. And then finally, if you look at the three colors, the green ideal, the blue warping, and the red aggressive, that those different types of behaviors play out and leave different repeatable signatures in each of those electrodes and in each of the different fingers. And so that's what our algorithm will learn. So here's the video of the different behaviors. And with enough policy updates, we can take some of the nominal trajectories that were learned and then apply them to different contexts or different page sizes. So on the left-hand column, you'll see the very first time that the robot attempts to do this task. And then on the right-hand side, you'll see what we believe is, the ideal learned policy.
But is an update just one try? Or
I believe that there might be 40 rollouts within each update. I'd have to double check those numbers, but it's not just one attempt. Okay, I've got two more points I want to make about touch. One is that touch is shareable. And so about a month ago, I was at the ICRA conference, and I had the privilege to test out this tactile telerobot, where we have these shadow robot hands with now smaller biotach fingers, biotach sensors, and I'm controlling them using my motion, but I'm also feeling what the robot fingertips are feeling through the Haptic gloves that use pneumatics. So the point is that robots can collect these tactile sensor data, but you can also share touch remotely to operators. And so I thought I would kind of bookend this talk with a follow-up visit to Dustin Tyler's lab and how we're thinking about touch with our new collaboration.
Brandon Presswood lost his arm in a workplace accident in 2012 and is also a participant in Tyler's study. He too had surgery connecting his nerves to sensors in the fingertips of a sophisticated prosthetic limb.
Basically, they've mapped where if they put this electrical signal to this contact on the nerve cuff, then that makes me feel a pinprick in my index finger.
But he doesn't even have to wear it to get that feeling.
The fact it's attached to his arm is actually kind of arbitrary. We can put the prosthesis anywhere in the world, and he would still feel like his hand.
Prestwood is trying out the idea with his prosthetic arm mounted across Tyler's lab.
And so now we can extend his capability. We can essentially amplify the person by taking that sense of connection, the sense of touch, and putting it on any machine in any part of the world and bring it back to your nervous system. And then I can connect it to devices that can do far more than my weak biologic system.
Okay. This brings me to my last point, which is touch is connection. And so for most of my career, I've thought about touch from a very task-oriented base, not so much social connection. And of course, with the pandemic and, not being told not to shake hands or hug or anything like that really highlights the importance of touch for social connection. Whether you're interacting with a newborn or your loved one, or even meeting new people at our workshop. And so recently I've begun collaborating with Dustin Tyler. He's at Case Western Reserve University. He has started the Human Fusions Institute, and the goal is to directly connect the human and the robot using what they call neural reality, to enable humans to be physically in one place and experientially in another. And the goal is to transcend the use of robots as tools, remote tools, but to actually enable embodiment. So, you close your eyes, you log in, you open your eyes, and now you're physically in this whole new place, using your own body to physically interact with agents and objects in that new place. And I should say that the idea of telepresence is not new. It's been around for a while. I believe it was started by researchers in Japan. And more recently, there's been interest, especially for the Avatar XPRIZE, to develop a system that enables this remote embodiment. And so I guess a little more than a year ago now, we threw our hat into the XPRIZE Avatar ring and started to build a system that will allow an operator at Case Western in Cleveland, Ohio, to embody a robot in our lab in UCLA. And so this is a video showing two of the student leads, Luis in Cleveland, Lionel in Los Angeles, shaking hands and meeting remotely for the first time. I'll show you a little bit more about the robot embodiment in the next couple of slides, but the operator is receiving tactile feedback via an electro-tactile glove that they've developed.
I can also move it up and down. Could we do a touch test, please? Yeah, thumb, index, cool.
The recipient and operator can also work collaboratively through the avatar system to perform shared tasks.
Okay. Let's have a toast. Cheers. Cheers.
Performing a toast was one of the tasks that we were supposed to do to earn points in this competition.
But I'm a little, Veronica, just so I understand better, what's going on? Is the remote person wearing a glove or manipulating this thing? I don't quite understand.
Yes.
Are they getting feedback?
Yes. So the operator in Cleveland is wearing an Oculus Quest that's tracking their head motion as well as their hand movements. They're wearing an electro-tactile glove for haptic feedback. They're also wearing a white glove on top of it to enhance the hand tracking. And as they're moving around, that's moving the gripper and the arm in Los Angeles. That particular robot version was an old version that was a simple 1 degree of freedom gripper that had gel site wedges. And so each of the gel site fingertips provides tactile feedback to the operator in Cleveland.
Okay, yeah, thanks.
Yep. So we made it to the semifinals in Miami. This was less than a year ago, and that was fun because most of our team members met in person for the first time. It was a teleoperation team that really was started over the internet. And this is testing in our team garage. This is Dustin Tyler shaking the hand of, or interacting with a postdoc from my lab who's embodying the robot from a completely different room.
Yeah, I'd love to. Nice to meet you.
Very nice to meet you as well. Welcome to LA. It's good to see you.
Thank you.
So,
Pleasure to be here.
Oh, that's great. So I'm curious to see how well can you move your hand? Can you flex your wrist?
Let's see.
Oh, that's great. Good. Perfect. Extend. You go the other way with it. Excellent. Good. So now you're supinating. That's good. Can you rotate it up? Perfect. Can you rotate it down? Natural. Awesome. Bring it back. So my job is really easy right now.
So for the actual judging, we had judges with expertise in a variety of haptics, robotics, social interactions come in, and we were randomly assigned someone. We got them suited up. They got their electrotactile glove, the Oculus Quest, and then in a completely different room, we had our avatar. So our robot avatar was built upon this human-safe platform called the Stretch Robot from Hello Robot. So it's purposely got a very small footprint because mobility was also a way to get points in this competition. And we focused on 2 particular upgrades. One is a binocular camera to give the operator stereo vision and depth perception, but also to enable some eye contact because the 2 lenses actually look like eyes when you're interacting with that robot. And then we also wanted to upgrade the standard kind of passive gripper that the robot came with something that looked a little more anthropomorphic. So we used a Tasca prosthetic hand, and then we outfitted it with additional force sensitive resistors. So they're not the fanciest tactile sensors, but by enabling the visual tactile synchrony, it's still pretty powerful. And so we went with that system. And we made it to semifinals. The finals will not be going to them, but they'll be hosted in Long Beach in this November, and we plan to go visit and see how everything turns out. But I'm very pleased with our semifinals entry because it number one, established a formal collaboration and with a variety of research teams across multiple universities, but also now we have this system that enables us to ask all sorts of interesting questions. And if you're really interested in touch, I encourage you to check out this June cover issue story by Cynthia Gorney and Lynn Johnson. Cynthia Gorney interviewed 15 to 20 researchers around the world to put together this story, and Dustin and my team were very honored to be included. But it's a really beautiful piece on the social and functional task-based aspects of touch. So I thought I'd leave you with just some exciting directions of things I see related to touch and socio-physical interactions. One, I've seen more recently groups that are combining proximity with tactile sensors using cameras or other types of combinations of sensor packages. I think that one of the things that we really need are better simulators for tactile sensors. And so working on the sim to real, as done by Carlos Sferrazza and Raffaello D'Andrea, is a promising way to do that. Also using robot avatars that enable inclusion and full participation in the workforce, enabling individuals with impairments to remotely operate robot avatars, as in this cafe, to not only have a job, but to interact with others, I think is a wonderful direction that we're headed. And finally, robots for socio-physical interaction. So there's been social human-robot interaction. You can think of robots that were designed for autism, for example. There's been physical human-robot interaction, such as humans and robots grasping the same table and manipulating it together. But this new frontier of socio-physical interaction, I think, is really exciting. And you know, what's shown there is my postdoc Alexis Block, who studied with Catherine Kuchenbecker, among others, to develop a human scale haptic device called HuggyBot. And so not only did she have to figure out, you know, how to do the timing and the strength of the robot and all of that, but she's been measuring cortisol and oxytocin to also look at the physiological benefits of social touch. And that leads me to my last slide, which is there are some upcoming workshops that might be of interest to this particular group. Kiara is going to be speaking at both of these. There's the National Workshop on Human-like Robots, as well as a workshop that I'm helping to coordinate at IROS in October. And that's on large-scale robotic skin. So if we're going to be thinking about human-scale haptics and human-scale interactions, we're also going to need to scale up the areas that we're putting sensorized skin. And I believe that virtual participation is available for both of these. All right, so I'd like to thank the students who did all this hard work, my collaborators, as well as our funding agencies. And thank you for your attention.